This video continues our look at the audio analysis tools provided by the Synesthesia plugin. After the last video where we demonstrated how to implement the tools, this time we're going to talk through the Mushroom Music Blueprint as a case study in how you can use them for a slightly more sophisticated result. We've got the usual collision sphere overlaps and interact key to start the system. The audio playback is handled here, and the actual use of the analysis data to affect the visuals happens over here. The reason that this playback system is more complex than the last video is that this time our musical loops are not neat patterns that can loop around from the end straight back to the beginning. This time our musical sound waves have decay tails, since, as any jazz cat can tell you, tails are important. If we have a look at one of the musical stems, we can see why. So that's got that drum hit just at the end of the second bar. Now if we were going to create a perfect loop, we'd split it there and we'd simply loop around those two bars. So musically that works, but we lose that tail. So instead what we're doing this time is we're exporting 3 bars of music, so we've got that nice decay tail at the end, and we're re-triggering another copy of it over itself. So by re-triggering, we keep that impression of a loop, but because we've got those decay tails, the music's going to sound a lot smoother. However, the consequence of this is that we need 2 audio components that will run in parallel, so that we can have a new one start while the old one is still playing out the tail. We use a timer to trigger the audio events every 6.233 seconds, so that's the length of 2 bars, and this goes to a flip-flop, so that the first time our sound cue is played on audio component 1, and the second time it's played on audio component 2. So we add an audio component to the blueprint and we assign it to the variable AC01. We bind an on audio playback percent to it, assign our sound cue to it and play it. We'll come back to this bit later. We also bind an event to on audio finished so that we can destroy it when it's finished playing. This means we don't have lots of audio components sitting around not doing anything. Finally, we check the other audio component and unbind it from the audio playback percent events so that we don't get the data from the tails as they play out, just the data from the start of the new component. From our on audio playback percent events, we get the names of the sound waves that are actually playing, since our sound cue is randomly choosing from different combinations, as you can see here. We check the sound wave names to control a series of branches. When the appropriate string is found within the sound wave name, these functions route the events, the name of the sound wave, and the playback percent to our different custom events for our different systems. The next time our music is re-triggered, we do all of this again, but using a new audio component. And again, unbinding the playback percent event from the first component so that we don't get that overlapping data. The first system controls the size of various visuals using the loudness values from the synesthesia assets of each sound wave. From the custom event, we get the length of the sound wave name and chop the whole string away until we're just left with the end value. As you can see in our sound cue, all the sound waves are named such that the end value gives us a number, 1, 2, 3, 4 in this example. This is the number that's left after this right chop chops away all of the string apart from the last digit. And this is used to control the index of this select node. The select node options are the synesthesia assets for each of the sound waves. We get loudness at current time by multiplying the total duration of the sound wave by the current playback percent, map this loudness to an appropriate range, and use this to scale the brown mushroom actors, in this instance, in the level. These have been assigned using the public variable kick mushrooms. The snare and pizzicato systems work in exactly the same way. As our audio playback percent events come out, we check the sound wave. If it contains the substring snare, then we send the values here. If it contains the substring pizz, we send the values here. And again, we chop the name of that sound wave to get an index number that controls our select node. I'm just going to solo each of those in turn. So there's our kick, controlling those brown mushrooms. Now we've got the snare. And finally, the pizz is controlling that particle system. The flute custom event controls the purple mushrooms, which emit steam whenever their note is played. You might have noticed that there are 13 mushrooms, and these are aligned to notes going from C6 to C7. Again, we're using the last item of the string name to select the correct synesthesia asset. This time the synesthesia assets are of type constant Q. And if we look in the settings, we can see that we're looking for 13 bands or 13 notes starting at the frequency 1046.5 Hz. This is the frequency of the note C6, and all of our flute lines fit in within that octave. So this array has 13 elements, 0 to 12, and these hold the magnitude of the 13 notes being detected. So in effect, the index of this array is the note. So index 0 is C6, index 1 is C#6, etc. We use these indexes to control the 13 emitters that are held in the public variable flute mushrooms. We get the max of float array, in other words the loudest current note, and check the magnitude is above -35. If it is not, then we'll assume that no note is being played and we'll deactivate the last emitter. And if it is above -35, then we'll assume that a note is being played. This system here checks for held notes. It compares the new note to the last note that was played, and if they do match, in other words the branch is true, then it does nothing. If the two notes don't match, we turn off the currently active emitter and activate the new one. So all of that is just being generated by the synesthesia constant Q analysis and this system here. Finally, let's look at the hi-hat system. This one works slightly differently. Back where we trigger the audio, the first thing we do is choose a random integer and set that to the variable random hats. This is then used to determine which hi-hat sound wave plays within the sound cue by using the set integer parameter node and controlling this switch. We determine which hi-hat sound wave will play at this point because we want to actually set up the hi-hats in advance of when they actually play. So this scan onsets function here triggers a custom event within our hi-hat section. The great thing about non-real-time analysis is that we have the data already, so we can use this audio analysis data to actually build things in our game world. The placement of the yellow mushrooms in the game is actually determined by the analysis of the audio onsets within the sound wave files themselves. So the first thing that our hi-hat system does is it checks to see if there are any hat mushrooms already in the level and destroys them. It then uses that random hats variable to choose the correct synesthesia asset. Then it gets the timestamps and strengths of the onsets in that file, and it uses these to spawn a series of mushrooms, using the time to place them and the strength to determine their heights. So this section creates all those small yellow mushrooms in the level, and they're laid out following the patterns in the hi-hat sound waves. As they're created, they're added to this spawned mushrooms array, and then we use the custom event hats that's triggered by the audio playback percent node to check through the onset data and compare these onset timestamps against the current playback time. If they're nearly equal, then this system here activates a light within the mushroom hat's blueprint. The hats are played in 16th notes, and the duration of the analysis is 3 bars, since we have a bar for the tails as well. So if we divide this duration by 48 to get the length of one of the 16th notes, we can multiply this by 0.1 to get a 10% error tolerance here. So you can see there that the layout of the mushrooms changed instantly the minute a new sound wave was picked. Using this analysis data to inform the layout of items or even the design of a game level itself has lots of interesting potential. In the last 2 videos, we've seen a number of ways in which the synesthesia tools can provide audio analysis that's perhaps easier to understand and use for musical applications than some of the other approaches that we've covered. There's a huge range of potential applications for these, and hopefully you can put them to some really creative and imaginative uses.